About the ACES mission. It comprises of a laser-cooled cesium beam clock and a hydrogen maser several-time transfer system. It's scheduled to launch soon in the second half of next year. And so there's been a lot of characterization. One of the important things for ACES is, for the ACES mission, is the accuracy of the PHARAO cesium clock. So there's been a lot of work on that. Most of the work, of course, has been done by the Paris group, Philippe Laurent, and so there's quite a few different systematic errors, and then there's a couple where we're contributing, and so those are on the cold collisions, cavity phase, and microwave lensing. This is an earlier accuracy budget, and so I'll show you the progress on this. First, talk about the Doppler shifts, frequency shifts from cavity phase variations, and then the collision shift. And the point here is that we're going to group these two together, it seems, and extrapolate in both density as usual, but also as a function of launch velocity, and that will give an extrapolated frequency which takes care of both the cavity phase and the collision shift. It then becomes a statistical error, mostly, we expect, and not a systematic error per se. So I'll talk about that, and then we finish the evaluation of the microwave lensing frequency shift for PHARAO. So I'll update these at the end. And again, Philippe Laurent, Christophe Salomon have done a lot of work on this. Christophe is the PI. And in my group, Phil Peterman is a graduate student who's done much of the finite element work for these, the cavity phase shifts. So distributed cavity phase shift in a fountain, for example, let's just look at what is done in fountains. The atoms go up if there's a phase gradient across the cavity. For example, there's power being fed in if it's fed from one side or the other, or there's an imbalance there. And also just because the power is fed in from the sides and absorbed on the walls, there are phase gradients in the cavity. So if the atoms go up and come down at two different places, on average, there's a difference in phase. That times your line width gives you the first order Doppler shift. So the way that we treat this for the fountains is we expand the field as a standing wave, the thing that you would like, plus a loss field that accounts for the wall losses and the feeds. And so that's the standing wave plus the loss field. And one of the key things that we do is to solve for both fields independently. The standing wave field is about 10,000 times larger than the loss field. If you don't solve for them separately, you have numerical errors from the standing wave field leading into the loss field. One of the difficulties for this is that near the apertures of the cavity, the fields are nearly singular. There are large currents that run in the copper right at the corner as the magnetic flux. Microwave magnetic flux tries to escape through the hole, and so the fields diverge down to if that corner is very sharp, the fields diverge down to the skin depth, 0.7 less than a micron in copper. If there's a rounding of this corner, it diverges down to the scale of that radius. So that means you have to mesh quite densely. That gives you a relatively large finite element models. This is all really very stringently tested in the fountains. A number of groups have tested this, and the most stringent one is by Sirt in Paris. So in the fountains, we have the fields, and now that the way that you assess the distributed cavity phase shift in the fountains, it's different than what we need to do in PHARAO. And the key thing is to expand the loss field into an azimuthal Fourier series. And that is useful because the higher order terms, the field at the center of the cavity grows as rho to the m. So for high powers of m, for m equals 3, for example, essentially that's negligible. So you only have to consider the first three Fourier modes, the azimuthally symmetric phase, and this ends up being a longitudinal phase shift. Potential unintended phase gradients, these we measure by tilting fountains. And then quadrupole variations because the power is fed in on opposite sides and then net absorbed on plus and minus 90 from the feeds. So the m equals 0 and the m equals 2 can be calculated, and then the m equals 1 is measured. The m equals 0, it's really not the transverse phase that matters, but it's a longitudinal phase. And so here's the longitudinal phase. This also really isn't that important. What matters is potential gradients top to bottom. And so if the top end cap of the cavity absorbs more than the lower end cap, our uncertainty about that sets the limit for most of the fountains. And so in the fountains, we specifically evaluate each one of these terms. It's really very rigorous. That approach is difficult for PHARAO. And the reason is that you have two microwave zones, and there can be a different unintended phase gradient in each zone. To measure that, you'd have to be able to controllably move the source around in this zone, keeping it the same in that zone, and vice versa. And so we don't have that capability in PHARAO. We don't have the capability to feed from one side or the other side and to exaggerate the shifts. And so instead, what we can do is use the dependence of the Doppler shift on the launch velocity. By going very slowly, a long time, the line width gets narrow, then the Doppler shifts have to become smaller. So the phases are what is fixed. If you go to a long time, a small phase difference matters less and less. So here's a model of PHARAO, and one way to think about PHARAO is that, so again, it was designed before 2004 when we really began to understand a lot more about the microwave fields in the cavities. Feed comes in here and goes out to either end. So there's net power traveling towards each interaction zone. If you think about that as a fountain, what would it look like? What it looks like is a fountain cavity that's fed from the top end cap. A lot more about the microwave. So the power comes from the top. There's a phase gradient vertically in the cavity, and so that gives that longitudinal phase gradient gives you a power dependence, and it's a unique power dependence. It's not one that we see in the cavity, but it's one that does lead to the uncertainty. So this difference in the end caps potential resistances is what sets the errors for the fountains. But here all the power comes from the top, not a small percentage. In PHARAO, these corners may be as small as, we expect that they're as small as 20 microns. So again, the fields diverge down to the scale of that radius. This cavity is 25 centimeters long, and you have potential divergences at 20 microns. So the tetrahedra to mesh this for convergent fields need to be as small as about 3.5 microns in a 25 centimeter cavity. It doesn't have cylindrical symmetry, so you have to do a full 3D FEM. We end up then being able to solve it, just barely, with 27 million tetrahedra and taking a terabyte of RAM. So that's all that we have available, and we use all of it. That gives really very nice fields, and so here's the standing wave field in the cavity through the mid-plane as a function of the transverse position, x and y. And then if we go near the top, this is the loss field. And again, you see these singularities, and here you see the phase gradient through the middle of the cavity because the power is fed from the middle towards each end. Go to a little bit higher or a little bit lower, the fields basically look the same. And so we have really nicely converged FEM solutions. So again, the frequency shifts decrease as 1 over the time, that is as the line width, or 1 over as the velocity goes lower, the frequency shifts are proportional to the launch velocity through the fountain. And so as you go slower through the fountain, you get smaller frequency shifts, and that's for the distributed cavity phase, the phase variations in each zone, as well as any end-to-end phase shift, the difference between the average phase in both interaction zones. Naively, again, you would expect that the Doppler shifts would be proportional to the velocity, and that includes the launch velocity. So if you have a cloud offset, for example, then the faster you go through, okay, then you can, again, same phase shift, but if you go through faster, then you have a shorter time and therefore a bigger frequency shift. And so here's for example, the shift that we expect from the known wall losses in PHARAO. And one thing that you can also have in PHARAO is a different average microwave amplitude in each zone, because they're not the same as in a fountain. And that actually leads to pretty big frequency shifts. So on the ground, we can set limits at the level of plus or minus 5%. We don't expect it to be that large. Even if it is that large, you can see that as a function of velocity, you can extrapolate back to a frequency shift that's well less than plus or minus 1 minus 16. So that's not a problem. If we have phase gradients in a zone, here for example in the second zone, so this is for a difference in resistance on either side of the cavity of 10%, then that will produce a phase gradient, and now the frequency shift can be quadratic in the launch velocity. So for example, if you have an offset of the cloud position down here, if you go really slowly, then the cloud expands a lot, and the net offset in each zone essentially goes to 0. So as you go slower, that offset gets smaller, and then the frequency shift decreases more quickly. So the frequency shift can be quadratic. So that's for an offset of plus 2 millimeters. You can be offset in the opposite direction, and then basically you get the opposite frequency shift. You can also have a launch misalignment, so you can launch in a slightly different direction, plus or minus, again, basically opposing frequency shifts. And so we calculate the known losses, the things that we know are there, and those aren't a problem. Okay. In addition, we calculate the sample fields for phase gradients, and then look at a lot of different things. For example, launch angles, position offsets, detection, selection, inhomogeneities, detuning of the cavity as the gray curve, the different pulse areas. And so we look at all of those, and what we can do now, because it looks somewhat quadratic, is we can extrapolate the clock's frequency versus the launch velocity. Again, as you go to 0 velocity, you expect the Doppler shifts to go to 0. And so you can see here that all of these different effects, these are sort of the worst ones that we see. The difference between the linear and the quadratic can be a fraction of 1 minus 16, but less than 1 minus 16 for the sizes of effects, worst case effects. And so the expectation is to take 3 different velocities here, about 0.6 meters per second, 1.5 meters per second, 0.6 meters per second, and something around 0.2 meters per second. Use those 3 velocities, fit that to a quadratic, use the lowest 2, fit that to a linear, and that's what you see here. And then with that, the differences between those is again less than 1 minus 16. We'll take the average of those 2 extrapolations as the clock frequency, and then the difference and its instability as the clock error. We expect the instability to dominate. So in the end, we expect to end up with a statistical, not systematic error from the combination of both collision shift and cavity phase. Each one of these measurements at this velocity versus velocity has been already extrapolated versus density. And so that accounts for both the collision shift and the cavity phase shifts. So the bottom line is that, again, the known effects are less than 1 minus 16, and it looks like worst case effects can also be extrapolated to less than 1 minus 16. On microwave lensing, so microwave lensing, again, now for the fountains being at 1 minus 16, they have to be considered as atom-interferometers at that level of accuracy. And the same for PHARAO. So what happens in a microwave clock, for example, the convenient basis here is to look in the dress state basis. If an atom enters in the ground state, it's in a coherent superposition of the 2 dress states. One dress state sees a focusing potential by the microwave standing wave. The other dress state sees a defocusing potential. So one dress state, the blue state, is focused, the red state is defocused, and then on the way back down, the second Ramsey pulse, transition probability versus frequency, here's your Ramsey fringe. On this side of the Ramsey fringe, when you come back down, what the Ramsey fringe does in the dress state picture is it takes dress state 1, the defocused state, and puts it into the excited state. That's what you detect. On this side of the Ramsey fringe, what the second interaction does is it takes dress state 2, the focused dress state, puts it into the excited state, and that's what you detect. So because you detect more of the focused state through the apertures of the cavity than the defocused state, the transition probability on this side is higher than on that side, and that's a frequency shift. And so it's all about the apertures, and here the important thing is that the atomic wave functions are localized to less than a microwave wavelength, and so it doesn't act like recoil shifts, but the apertures play a key role, and it acts like lensing. So in PHARAO, there's 4 apertures. So we have apertures at the beginning and the end, and then due to those divergent fields by the entrance and exit of the cavity, smaller masks were added late in the game, and those are about 400 microns smaller in each dimension. And so there's 4 separate apertures, in contrast to fountains, where essentially there's 1 aperture at the beginning and 1 aperture at the end. And those lead to some different effects. As well, there's dipole forces in both interactions. In microgravity clocks, these interactions can be more important than in fountains. Still, we find that they are negligible. And so here's a summary of a number of fountain clocks. And most fountain clocks have microwave lensing frequency shifts between 6 and 9 minus 17. PTB, an evaluation that's in works right now, just because of its geometry, it's a little bit lower, but all the others are basically 6 to 9 minus 17. All of these clocks apply that correction, NIST does not. And PHARAO ends up being significantly bigger. So instead of 6 to 9, it's about 11 and a half plus or minus, and we assign an uncertainty of about plus or minus 4. Essentially, this is pretty conservative. So many of you probably know there's some recent controversy on microwave lensing coming from NIST. And so the history of the microwave lensing or microwave recoils dates back to 2004. Peter Wolf and Christian Bourdet essentially treated discrete recoil shifts. And I treated the microwave lensing, and then in the last year, NIST has treated this as well. If you point to any fountain in the world and ask what does each one of these predict for that fountain, you get 3 different answers. So 10 years ago, Peter and I have understood the differences between our treatments. When we go through those, we can come to a situation, a realistic physical situation, where we should agree. When we do that, we do agree. So again, we predict something like 6 to 9 for several fountains, and for NIST F2, for example, we predict a 9 minus 17. This is on the order of the accuracies of these standards in space. NIST, on the other hand, this treatment predicts a shift between much significantly smaller, between 1.7 and 2.9 minus 17. We have identified specific problems in the NIST treatment. There's several different problems we've identified. Without addressing these issues, NIST has reaffirmed their calculation, and they've used some strong words to describe our work. In the limit of weak fields, our treatment connects smoothly to recoil shifts, which are, of course, well known in the optical spectroscopy. And so here is frequency shift as a function of the size of the apertures, scaled by the size of the cloud at the end of the fountain, or whatever experiment it is you're doing, and the size of the initial wave packet. And so for fountains, we have small wave packets and apertures that clip the cloud significantly. So you're down here, this is the microwave lensing regime. As the wave packets get big and span many wavelengths of the field, you go to a recoil shift, and then to the value of a recoil shift. In an actual recoil shift, you actually have to have no clipping of the wave packets and resolve the different paths. And so in this limit, you get a recoil shift. Again, that gives us quite a bit of confidence in both the scale factors here and size in the calculations, along with, of course, the agreement with Peter Wolf, which was really a very independent calculation. The NIST treatment cannot recover recoil shifts, and so they do not have that check. So anyway, this has been going on. This controversy has been going on for a little while. Most clocks, depending upon how you count, 9 or 10 out of 11 or 12, 11 or 13, let's say, correct for the frequency that we calculate. They've heard the remarks and read what's been written and continue to make these corrections. There's 5 more evaluations in progress, including PHARAO, again, using our treatment. How much? Okay, I'm getting near the end. So The different apertures in PHARAO, because these 4 apertures, you can look at how the shift depends on those. And in the end, there's some interesting differences, interesting behaviors, but all the differences here are really relatively small, and they behave a lot like the way that they do for fountains. And so you can put in some different corrections, and the blue here is the final. The end result of the shift is, again, something like 11.5 minus 14, up to as big as 13 times 10 to minus 17. All right, and so to summarize, again, there's the microwave lensing shift for PHARAO. We calculate the fields for PHARAO and the known distributed cavity phase shifts. We can group the unintentional phase gradients with the known gradients, as well as any end-to-end phase difference, group all that with the collision shift, extrapolate versus density and launch velocity, and we think that the error can be below 1 minus 16. That will make the cavity phase and collision shift in a statistical error and likely negligible systematic error. We'll have to do the final analysis, of course, once we have the final parameters on orbit. And so here's the error budget. And essentially now we know what the bias of the microwave lensing frequency shift is. We have an uncertainty of about 0.4. Combining these two then, that becomes a statistical error. We believe it'll be below 1 minus 16. And so probably the total can be below 1 minus 16. Thank you.